So, Bismillahir-Rahmanir-Rahim. Now I'm sharing a screen for you, and this is topic. Today's topic is chapter 11, impulse turbine, impulse steam turbine, where the topic will be power output of the steam impulse turbine. Today we will derive, we will draw velocity diagram of impulse turbine at inlet and outlet of the blade, single stage impulse turbine, which is called as Laval turbine, and you will see how power can be calculated with the help of velocity, magnitude, and velocity angles and blade angles. So this is the procedure. We draw velocity triangle that inlet and outlet of the blade, and with the help of that velocity diagram, we calculated force acting in tangential direction and actual direction. Tangential direction force is responsible for work done, and axial direction force is responsible for axial thrust. So this we will derive. For that you have to do very carefully notations, know about the notation, understand the notations, how notations are done. So without understanding notation, you cannot understand velocity diagram, and what is symbols are used. You should know the meaning of that. So can you see the screen? Screen is available.
Yes, sir.
Okay. So my lecture notes are visible to you. Then it's okay. Let me zoom it in to make it bigger for you. And I recommend you to please don't see my lectures or any other lecture on small screen on mobile. You should see it on bigger screen, and you should use your laptops or desktops. Now, first of all, yesterday I told you that these things you have to revise. Fundamentals of mechanics, I'll not revise it again. And these things you should revise. How vectors are shown, what is the meaning of these straight line with arrows, and they represent velocity. The length is equal to magnitude of the velocity, and arrow shows the direction. So this is important because you have to draw in order to design, in order to do numerical problems, and in order to design actual blade. So you must know how to draw velocity diagram with pencil and paper and straight edge, that is scale, a futta, and a protector to make an angle. So with the help of straight line and angles, you can draw a triangle which is called as velocity triangle. So for example, this is a velocity triangle. One vector A, vector B, and vector C. A plus B is equal to C. So you will need these things. And there are in trigonometry, some laws are there, trigonometric identities. For example, if two sides in one angle is known, we use sine, law of sines, which is written here. It is sine A upon A, sine B upon B. So angle, sine of angle divided by side opposite to that, they are equal, and this is called law of cosines. If one side is known, the other two sides are known, and angle between two sides is known, then you can calculate third side, which is written here. No, don't do it. My class, hello. Let it work. Don't go to electricity, okay? Sorry, my electricity was gone and we are working on generator. And now light is come, so I stop because the lecture will get interrupted. So I will be working on generator, no problem. So here, power output. So after knowing these fundamentals, this is just for your convenience. I have revised your trigonometry and geometry of metric examination. So our objective will be derive relationship of power output of steam impulse turbine. This is called simple impulse turbine, simple steam. Remember, we are talking about steam impulse turbine, not gas impulse turbine. Gas impulse turbine will come later, and they are designed like that but differently. Their notations are different, their angles are different, their angles are measured differently, their triangles are drawn differently. That's why This is, remember, this is steam impulse turbine, and one stage, simple, it is called simple steam impulse turbine. That means single stage. There is no velocity compounding, or there is no pressure compounding. So now power, we have to prove that power output of a single stage impulse turbine is equal to mass flow rate multiplied by blade velocity multiplied by change of velocity in tangential direction, which is called as delta CW, or change in whirl velocity. Whirling means rotating. So rotating velocity is in the direction of tangent to the top of the wheel, to the circumference of the wheel. At any point, tangential velocity to the circumference of the wheel is responsible for moving it, for rotating it. So here three triangles are shown, 1, 2, and 3. Actually, it is one left in this triangle is AOB, triangle AOB, yeah, ABO, is triangle at the inlet to the blade, and this triangle AOC is at the outlet to the blade. So this diagram is combination of both two, A and B. So velocity triangle at inlet plus velocity triangle at outlet, they are combined together because they have one common base, that is CB. CB is the blade velocity. Blade velocity is common in both of the triangles, so they are equal. So you can join OA with OA of each triangle, and in this case you get this diagram. And this diagram you can see the right hand side is shown positive, and downward is positive. If it is left hand side, then it is negative, and upward side it is negative. So this is notation for the vector, and here you can see that angles are shown, alpha and beta. Subscript I means alpha means velocity angle, velocity of steam angle, which is makes with the blade at the inlet. So that is why I for inlet and E for exit. So alpha I, beta I. Beta I is the velocity, relative velocity to the blade. It makes with the blade. Angle between blade direction CB, angle with direction CB, this is, and the direction of the relative velocity CR I at inlet, this is called beta, and beta I means beta at inlet, beta E means beta at outlet. Similarly here, this alpha E represents angle which it makes with CB on left hand side. This is alpha B, and this is the CB direction. A horizontal direction is CB direction, and this is the exit velocity vector. So this vector is making horizontal direction angle alpha E. This is called air velocity angle at the outlet. Beta E is the velocity angle, blade angle at the exit, because relative velocity is the called as blade angle. Angle between CB, blade velocity vector, and relative velocity of air vector is called blade angle. Now this is combination of both, and here you can see that this line FB at the bottom, FB is the total length, which is equal to delta CW, work velocity. This is sum of delta CW1 plus CWE. So they are sum because this is difference. Actually, it's difference, but this is sum because they are in opposite direction. So difference will become plus. So CWI plus CWE. So one component of velocity at the inlet and outlet, that will be summed up numerically. These are the list of notation which I have already explained. When you will get this PDF document, you can read it at home. Now we will assume in our derivation following things. First of all, we assume that flow is frictionless. Steam, there is no friction between the steam and blade surfaces of the turbine. So another assumption is relative velocity at exit is equal to relative velocity at inlet. This is because of friction. There is no friction in the blade. So whatever is the relative velocity at the inlet, the same will be at the outlet. If there is no friction in the blade, this is assumption. And there is a factor called blade velocity coefficient, K. K factor is called blade velocity coefficient, and this is the ratio of CRE divided by CRI. and CRE is equal to K times CRI. Another assumption is beta I is equal to beta E. This condition is called as symmetrical bleeding. Condition of symmetrical bleeding. Blades are symmetrical when relative velocity of air at inlet makes angle with blade velocity equal to beta E. Beta inlet must be equal to beta outlet. So blade angle at inlet must be equal to blade angle at the outlet. Now we start the derivation. Derivation starts here from Newton's law. This is fundamental mechanics. Newton's second law of motion is F is equal to ma. So it can also be written as F is equal to ma m dot change of velocity in tangential direction. Because acceleration of wheel, we are considering how wheel starts moving. So how it changes the velocity with exertion of force. So that is called as tangential change of velocity in tangential direction. So rate of change of velocity is called as acceleration. So instead of ma, we write m multiplied by delta w. So change of velocity in axial direction, tangential direction. The tangential velocity of the steam relative to the blade at inlet is given by CRI cos beta. You can see the above triangle, and tangential velocity of steam relative to the blade and exit is AD in the above triangle, and this is in opposite direction. It is minus CRE cos beta E. Change in velocity will be velocity at the exit minus velocity at the inlet, and this is finally minus CRE cos beta E plus CRI cos beta I. Therefore, tangential force is equal to m dot से multiply करेंगे, m dot multiplied by change of velocity in tangential direction. So minus m dot CRE cos beta E plus CRI cos beta I. So the reaction to this force provides the driving thrust on the wheel. So this is actually force exerted on the air. Not, sorry, we are not talking about air turbine, gas turbine. We are talking about steam turbine. So you remember, I also sometimes forget. Remember, don't say air. So this is steam. So tangential force exerted on the steam is this one. That's why, and it has its minus sign. But force exerted on the wheel is equal and opposite. This is third law, Newton's third law of motion, that a force, for any force acting on a surface, there is equal and opposite reaction force. So this is equal and opposite reaction force. This is why minus sign will go, and we will write plus m dot CRE cos beta E plus CRI cos beta I. Referring to the combined diagram of above velocity triangle, we can say that AD plus A is equal to D, and this is delta CW, which I have told you in the beginning. Let's go back to that diagram. So here is that diagram. And this I told you that this FB, length FB, delta CW, CWI plus CWE, this is the force exerted on the wheel in axial direction, and this is called whirl velocity because it rotates, whirls the wheel. Whirling means rotation. So now we have derived this relation up to this point, and now we will go to next step. After this whirl velocity is calculated, now what about force? Driving force on the wheel will be mass flow rate multiplied by change in velocity. So this is also fundamental of mechanics, that m rate of change of momentum. This is rate of change of momentum is equal to m into v. So now change in momentum is delta v. So v is velocity in mechanics, but here we make c symbol of velocity. So delta c, m dot delta c means m dot delta velocity. So w means whirl direction, tangential direction. This rate of work done is done. This equation 11.2 shows the driving force. Now force into distance is the power. So force into distance the work, and force into distance divided by time is the power. So this was m dot delta CW. This was force. Though this force multiplied by CB. CB is again velocity. Velocity is the distance divided by time. So that is why we have a formula of power. So force multiplied by distance, m dot CW में force आ गया, m dot delta CW में force आ गया, और c में distance आ गया, और c में time भी आ गया. So this is actually power output of the steam turbine. M dot CB delta CW equation 11.3, and this was the objective of today's lesson. And with this we will finish. You should go through very thoroughly. I have already prepared the lecture in detail. Fundamentals of geometry, fundamentals of mechanics are mentioned here, diagrams are drawn here. Actual reading from the book will take a lot of time. So with this 2-page document, you have learned how to calculate, how to derive relationship of force acting on the wheel, steam turbine, and power, produce power output by the impulse steam turbine. Thank you very much. Here we will close our meeting.